In previous class, we discussed about briefly. We discussed about union set operators, set operations, right? Union, intersection, subtraction, Cartesian. So we can implement union by using union function or plus plus. Okay, let's take one simple example to demonstrate this set operations. So first, what I'm doing, I'm importing package, creating Spark configuration, setting master, and setting application name. And next one, creating Spark context, setting log level. Okay, so these all are presented in. We created one separate file, right? In our Spark application, Spark workspace. Here under core, we have imports file. In this imports file, we already created importing, setting configuration, master name, application name, log level. Okay, let's import this one. Open SBT cell, type console to start SBT. Okay, let's load imports.txt. It's import or imports? Imports. Type load space imports.txt. It will import txt file, imports a txt file. In that we return creating importing package and creating Spark context, right? Now load this file. So I'm loading file. File name is call log data. Let's go browser, and here 192.168. 0.47, I think 0.43:5070. Let me check ifconfig. So it's 173.44. 173.44. One 144. Go to utilities, go to browse file system. Here we have Qt. Under Qt we have call log file. So load this file. First load this file. Val rd1. So we take a name is rd1 equal to sc.text file. sc.text file and file name, file presented in hdfs colon slash slash 192.168.173.144 colon 8020 slash 8020 slash qt slash call log data. Next, let's count number of columns. rd1 dot count. We got count, right? Next what I'm doing, So get number of partitions. Get number of partitions, it will display number of partitions of that RDD. Okay, let's print RD1 dot get num partitions. Get num partitions. It will display number of partitions. I have two cores, that's why it assigned two partitions. I want to print 10 records. RD1 dot take of 10 dot for each println. So it is printing 10 records. This contain drop records, success records, fail records. So I will create three RDDs, one RDD for dropped, one RDD for success, and one RDD for failed. So I'll create different partitions. So I'm creating success RDD. Next one, failed RDD. So here I'm creating one failed RDD, and I'm creating dropped RDD. Drop RDD. So let's count to success. Success dot count. So these are the records. Fail dot count. So these are the records, and drop dot count. Drop dot count. So these are the records. When I perform union operation, when we perform union operation, when I perform union operation or intersect operation, subtract operation, and Cartesian operation, what will happen? So parent RDD contain two partitions. So we are performing concatenation union of two RDDs, right? Failure RDD and if we, any other RDD, success RDD. So success RDD dot drop RDD we are concatenating. So success RDD contain two partitions. Drop RDD contain two partitions. Finally, we'll get union. We'll get combination of both, right? So that's why what I'm doing, I'm increasing partitions. I'm increasing partitions for success and drop and failure. So for success, I'm increasing 5 partitions. Drop, I'm increasing 7 partitions. Fail, I'm increasing 6 partitions. Let's increase partitions. Success dot repartition, and I'm increasing 5. So it will return RDD. Next one, file dot repartition, I'm increasing 7. So val f equal to 7. Next, val drop dot repartition, repartition of 6. So val d, val d. So I'm doing repartition. Let's first print a number of partitions. S dot get num partitions. Get num partitions. So we got 5. Next, f dot get num partitions. F dot get num partitions. Next, d dot get num partitions. So these are partitions, right? Success has 5 partitions. Failure has 7 partitions. Drop has 6 partitions. And number of records we already count. Listen. Now, what I'm doing, I'm performing union operation. I'm performing union operation. Val union RDD, union RDD, then success dot union drop. Success dot union drop. So success contain how many partitions? 5. Drop contain how many partitions? 6. Union means combine, right? Combine. So here S dot count. How many records? D dot count. How many records? So these many records, right? What I'm doing, union underscore RDD dot count. So this one, right? 748263. 8263. Correct, right? 748263. So these are the partitions. So count is combination of success plus drop. So we see these many count. Next, union RDD dot get num partitions. Observe union RDD dot get num partitions. 11 partitions. Combining 5 partitions plus 6 partitions. Totally union RDD contain 11 partitions. 11 partitions. So simply so we have two sets, S and D. S and D. So S contain 5 partitions. 5 partitions. It contain 6 partitions. So whenever you apply union, so what will happen? We get one partition combines both S plus D, right? So it contain how many partitions? 11 partitions. So here assume 10 records. Here assume 20 records. 20 records. Finally, it contain how many records? 30 records. It contain 30 records. Combining both RDDs. Both RDDs. Combining both RDDs is called union. So this is union operation. Union. Okay. Next one. See, intersect. Intersect. Intersection operation returns only those elements that are available in both the data sets. Both the data sets. Elements presented in both the data sets. If you use intersect, intersect, what will happen? So this is my sRDD. This is my, sorry, uh, another RDD. Okay, let's take, assume this is union RDD. This one is union RDD, union underscore RDD. In this, assume this is dropped RDD. So what are common in both drop RDD, right? Both contain drop RDD. So let's take, instead of union RDD, let's take RD1. RD1 contain success comma drop comma failure, right? It contains success comma drop comma failure. So this one contain, let me take failure. So this is failure. So here this is how many partitions? It has default to 2 partitions, right? And failure contain how many partitions? 7 partitions, right? So it will return only both the common values, yes or no? It will return only the common values. Common values. So intersect returns common values. Intersect returns common values. Guess how many partitions we get? Do we get 2 partitions or do we get 7 partitions? Can anyone get how many partitions created for new intersect RDD? Is it 2 partitions or 7 partitions? How it will create 7 partitions? Because data is less, right? Data is less, but in both the data sets, data is matched data. It will return only matched data. You are saying it will create 7 partitions. You are correct only, Prasad. Answer is correct. It will return 7 partitions. It will return 7 partitions. So if you perform intersect between first RDD minus intersect second RDD, it will return highest partitions RDD. Highest partitions RDD. It will return highest partitions RDD. So we'll get 7. Let's see. Val intersect intersect equal to intersect underscore RDD equal to RD1 dot intersect RD1 dot intersect and failure. So it's not intersect, it is intersection. It is intersection of failure. So then intersect underscore RDD dot count. It will return only match record, right? Intersect, what is the name we given? Interact, not intersect, we given interact dot count. So these are the records. Let's enter get num partitions. Get num partitions. Get num partitions. We get highest partitions RTT. Okay. So intersection operation returns only the elements that are available in both the datasets. The RDD created intersection is map partition RDD, and the number of partitions are equal to maximum of RD1 comma RD2. So whichever max, it will return maximum of RD1 or RD2. Okay. Subtract. What is subtract? So let's take a subtract. Subtract. So subtract means, assume this is my RD1. 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 So this is my RD1. RD1 minus subtract RD. This is failure. Failure RDD. So RD1 contain two partitions and failure RDD contain seven partitions. Seven partitions. When you apply subtract, 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 it will minus RD1 with matched values, and it will return non-matched values from RD1. So it will eliminate all matched value from RD1 and RD2. It will return non-matched values. Then guess how many partitions it will create. So assume here we have 30 records. 30 records. In this, 10 records are matched. 10 records are matched. Finally, you'll get 20 records. 20 records. 20 records. Example like this. 1, 2, 3, 4 minus 1, 2. We get 3, 4. 1, 2 minus 1, 2, 3, 4. So matched, matched. But in first data set, there is no values. That's why it will return empty. Okay, let's see. Val subtract underscore RDD. Subtract underscore RDD equal to RD1 dot subtract RD1 dot subtract F. Next, subtract RDD dot count. RD1 dot count. F dot count. F dot count. So if you minus these values, we got this one. Subtract count. Okay. So if you minus failure with RD1, we get these values. So get num partitions. RD1 dot get num partitions. Get num partitions. F dot get num partitions. Get num partitions. And subtract dot get num partitions. Subtract RDD dot get num partitions. So it is returning 2. So it is returning minimum partitions of RD1 comma RD2. If you subtract F minus F dot subtract RD1, it will return maximum partitions of minimum partitions, right? So first RDD partitions, it is returning first RDD partitions, not second RDD. It's returning first RDD partition. Okay. Next one, Cartesian. Cartesian means if RDD contain Cartesian, Cartesian, Cartesian. Assume we have RD1 and RD2. Yes, Cartesian product. So RD1 contain 20 and RD2 contain 10. So this is RD1, this is RD2, RD2. So if you apply Cartesian, you will get result is 200, 200, right? So this is Cartesian RDD. Then assume this is success. Assume this is success one. So we have 5 partitions. This is failure one. We have partitions 7. Then guess how many partitions it will create. Okay, let's create. Let's execute this one first. S dot count. S dot count 643621. Next one, S dot sorry F dot count. Cartesian product is Cartesian operation is heavyweight process. Heavyweight process. It is never recommended to use Cartesian operation because it will create multiple duplicate values. So if you execute Cartesian, there may be a chance of out of memory because S contain these many records, F contain these many records. When you apply Cartesian, it increases many records, right? So it is never recommended Cartesian operation. Okay. Well, Cartesian underscore RDD equal to S dot Cartesian of F. Let me check spelling. S dot Cartesian of F. Now Cartesian RDD dot count. So it may take more time to process your query because it has to load all Cartesian data, right? So it may take longer time because there are many records. Many records has to be loaded in memory. Then it will apply count operation. So it will take longer time. It will take longer time. It is internally processing, will take long time because we have only 2 processors. We assigned 2 processors and memory maybe it's 8 GB assigned, 8 GB or 16 GB. 16 GB memory. In that 16 GB memory, 2 GB is allocated for Windows operating system, and for this one virtual machine I allocated 8 GB. It is taking longer time, right? So it is taking longer time. That's why it is never recommended to use Cartesian operation. Never recommended to use Cartesian operation. Next important topic is Aggregation operations. Aggregation operations. Aggregation operations. We have aggregation operations are reduce operation, fold operation, and aggregate operation. First, what are aggregation operations? What are aggregation operations? See, see, we have RDD. RDD has some partitions. RDD has some partitions. No, no, no. Not min, max, count. Those are SQL. Okay. So here aggregation operation, aggregation functions are different. So what are aggregation operations means? We apply some aggregation operations on partition level, results of partition level, and results of partition level. So this is one RDD, RDD, RD1. RD1 contains three partitions. So here I want to apply aggregation operations like reduce, fold, aggregate functions. Aggregate functions. If you apply aggregation functions, it applies on partition, and after applying partition, you will get some results, right? Sorry, you will get results, right? You will get some results. So aggregation operations applies on partition level and results of partition level. Aggregation operations applies on partition level and results of partition level. Results of partition level. Results of partition level. So here we have three aggregation operations: reduce, fold, and aggregate. Aggregate. We have three aggregation operations. Three aggregation operations. Three aggregation operations. Aggregation operations. Three aggregation operations. What are these three aggregation operations? Reduce by key, reduce and fold functions. Reduce and fold functions applies the same operations in partition level and results of partition level. Inside this reduce and fold aggregate, we can write custom logic. We can write custom logic. So whatever custom logic we write in this reduce, fold, aggregate, reduce and fold, these are applies, this custom logic applies in partition level and results of partition level. Coming to aggregate, partition level you can apply different logic. Results of partition level you can apply different logic. Aggregation operations, reduce and fold applies partition level same logic. Results of partition level same logic. Aggregate function, partition level we can apply different logic. Result level we can apply different logic. So aggregation operation has facility. Aggregation operations, some aggregation operations we can apply partition level and results of partition level same operation, and we can also apply partition level different operation, results of partition level different operations. So operation which is executed on the partition as well as results of partition is called aggregation operations. So Either same operations can be used on the partitions and results of partition, or depending upon the requirement, different operations can be applied on partition level and results of partition level. So here we have three operations: reduce, fold, aggregate. We can apply about two operations, partition level and results of partition level same. But aggregate operation can be used for separate operations on partition level and results of partition level. Results of partition level. This we will discuss tomorrow, because we'll finish all these three in a single class, so that you will get clear clarity. Before applying aggregation operations, all aggregation operations should satisfy cumulative law. Cumulative law means if you are applying addition operation a plus b, so b plus a also should be written same result. b plus a should be written same value. A into b should be equal to b into a. Then we call it as cumulative law. Why we are saying aggregation operations should be satisfy cumulative law means, assume here we have, for RDD1 we have three partitions, right? So can we say first partition will execute first, next to second partition, next to third partition? Can we give guarantee first partition executes first, second partition executes the second, third partition executes the third? Can we give guarantee? No, right? Because it is parallel processing, right? It is parallel processing. So partition 1 is executing by worker 1. Partition 2 is executing by worker 5. Partition 3 is executing by worker 10. So different workers are executing these partitions. Then we cannot say which partition completes first, right? Which partition completes first. That's why whatever the order of partitions complete, so results should be same. If you run first time, it may execute partition 1, partition 2, partition 3. Next time if you execute partition 3, 1, 2. If you execute next time 2, 1, 3. If you execute next time 2, 3, 1. Like that it is executed. So we don't know order of partitions execution, but the result should be same. It should not be changed. So it must follow cumulative law. Okay. So that's it for today.